You're looking basically at, rotating flapping wing systems, both for, force production in air, water, and also for energy extraction, again, air both in from the wind and from rivers.
So specifically, the cyclorotor benefits from thrust vectorability. So unlike a propeller where you can only produce thrust perpendicular to the plane of the rotation, here we can produce 360 degrees of thrust. Additionally, because of the favorable aerodynamic conditions across the blade, with the blades being positioned at the tip of the rotation, we get increased aerodynamic performance.
You can vector your thrust in any direction, full 360 degrees almost instantaneously, which you cannot do with a conventional rotor. And if you design the cyclorotors properly, we have shown that you can achieve higher hover efficiency than a conventional helicopter rotor based aircraft. And and moreover, cyclorotors are capable of very high speed forward flight, and it can utilize this thrust vectoring capability for agility, for gust tolerance.
I'm working on a small 30-gram cyclocopter. If you take a really small helicopter or quadcopter and take it outside on even a slightly windy day, it gets blown all over the place. But our preliminary research has shown that this thing could fly in higher winds, and so it could be more versatile. And another advantage it has is that your typical quadcopter has 4 degrees of freedom, the speeds of the rotors, whereas this has 5, so the speed of the tail rotor, the speed of these, and then the direction of thrust on each of these. So you can change the direction of thrust as you like. That means you can sort of use these as you would a tank tread and point them forwards and backwards, or just go straight forwards, whereas a quadcopter has to pitch and everything before it can maneuver, and that limits its maneuverability.
This is a vertical axis cycloidal wind turbine. This would be very useful in urban areas because it has a high power density, which means you get a lot more power and using a lot less space. And so in urban areas where you couldn't use a traditional horizontal axis wind turbine, you could use these on rooftops or in parks and cities maybe, and you could use a lot more of them and extract just as much, if not more, power than horizontal axis wind turbines.
Looking at tip vortices for cyclorotors. Tip vortice is very similar to kind of like a little vortice you'd see in a sink when the water is going down the drain. It's just a normal looking, almost like a tornado type effect at the end of a wing. And I'm doing analysis at the end of a cyclorotor, where a cyclorotor is almost a paddle wheel type flight system. So by looking at cyclorotor tip vortices, you can better understand the lift and the coefficients of lift associated with them.
The project that I'm working on is a 2-winged, hover-capable robotic hummingbird. And what's kind of special about it is that it uses what's known as wing kinematic modulation techniques for all of its control, for roll, pitch, and yaw control. And this is basically purely biomimetic. The tilting of the flat planes, the amplitude variation is all what you would see in a normal hovering hummingbird. This is mostly used for reconnaissance purposes or for some sort of gathering of intel. It would be the largest application. It can be also used for any case where you really want to be as secretive as possible when you do conduct your operation. For example, if you're doing like wildlife management, you don't want to frighten the animals with any sort of unnatural flying devices, right? You want to have a very biomimetic-like vehicle mode of gathering intel. The wings flap at 20 hertz, which is a very low frequency in comparison to quad rotors. The RPM of the rotors are in the order of thousands, so it's very easy to hear. They're very loud. It's very easy to hear from a very far away distance. So when this actually flies up, when I actually fly this, and the wings actually flap up, It's very quiet, and a lot of people have remarked on how quiet it really is because it's at such a low flapping frequency.
Our robotic hummingbird is serving as a research platform, so we're actually using our robotic hummingbird to study flapping wing mechanisms, to study the unsteady aerodynamics around the wing, to see how is it that bees and hummingbirds and dragonflies are able to be so gust tolerant and agile, and how are they able to survive when strong winds hit them.
These concepts, might have potential for, much more agile, efficient, and robust flight compared to the quadrotors and helicopters that we see today.
It's an opportunity to innovate. It's an outlet for creativity, and it's really what I would consider to be a pioneering challenge in terms of the world of aerospace engineering, because something like a two-winged flapping wing system that is hover capable, I think could be the next generation of micro air vehicles.